Hello everyone, and welcome back to the ILTA Physics Online. Today, we're going to keep studying motion. In particular, we'll focus on some basic ideas of how to describe motion quantitatively. But before we start, let's quickly review what we learned last time. In our previous lecture, we said that kinematics is the field of physics that describes and explains motion over time using parameters such as position, velocity, and acceleration. We also introduced the four types of motion that we'll be studying: linear motion, projectile motion in two dimensions, circular motion, and rotational motion. Finally, we introduced motion diagrams, using the particle model to represent motion. This model was very useful because it allowed us to visualize motion clearly without needing artistic skills. So, with that review in mind, let's add today's new material. Up to now, we've been describing motion in a qualitative way, without using numbers or formulas. Today, we're going to take it a step further and describe motion quantitatively and mathematically. These key quantities are called motion parameters or kinematic variables. We'll begin with position and time, and then move on to displacement and velocity. Think of these as more formal versions of the everyday ideas of distance and speed. Let's go step by step. Let's move. All right, so let's check out the parameters we need to describe motion quantitatively. We defined motion as the change in position of an object over time. So when we analyze motion, we always focus on how an object moves during a particular time interval. In classical physics, we treat time as an independent variable separate from the motion itself. Now, you may recall from Einstein's theory of relativity that time and motion are connected, especially when dealing with very high speeds like the speed of light. But for our purposes in classical physics, we'll assume that time is independent. To describe motion quantitatively, we need to go back to the basics. Motion is defined as a change in position over time, so the two fundamental parameters are time and position. Position is the quantity that describes where an object is, which allows us to measure its location, whether it's moving or stationary. In everyday life, this is like giving someone an address or specifying a point on a coordinate plane. But since we are dealing with moving objects, we are also interested in the change in position, which we call displacement. We also sometimes care about the total path length traveled, which we call distance. Now let's include the time parameter into the concept of displacement. When we describe motion, we not only want to know the displacement, but also how long it took to move. That leads us to velocity and speed. Finally, if the speed of an object increases or decreases during motion, we need a parameter to describe that change. That parameter is acceleration, which we'll study in the next chapter. So, in summary, the basic kinematic variables are time, position, displacement, velocity, and acceleration. Up to this point, we still haven't really used any math, but if you've understood the concepts, you already know the foundations of how to describe motion quantitatively. From here, we'll gradually make things more specific using these 5 variables. Let's start with time. As we said, time is independent of motion. For convenience, when analyzing motion, we usually set the starting time to t equals 0. Next, let's talk about position. To describe the position of an object, we need to first define a reference point or origin. Then, the object's position is defined relative to that reference point. By convention, we can choose the reference point anywhere we like. It's up to us. So position is essentially a vector quantity because it has both magnitude and direction. For example, imagine 3 points A, B, and C on a number line. If we take point A as the origin, then B is at plus 3 meters and C is at minus 4 meters. That's how we define position. That's all there is to it. It's not so different from what you're already thinking. Now, when the object moves, its position changes, and this change is called displacement. Since displacement includes both how far and in what direction the object moved, it's a vector quantity. By definition, displacement equals the final position minus the initial position. Let's think back to the same example from the previous slide. If an object moves from A to B, the displacement is plus 3 meters. It moved 3 meters to the right. If it moves from A to C, the displacement is minus 4 meters. It moved 4 meters to the left. So far, this sounds very natural, but here's the important point. This is the first time we are using a formula, but notice it's just simple subtraction. This shows that math and physics is simply another language for expressing the concepts we already understand. Now let's think about distance. Distance is the total path length traveled, regardless of direction. Unlike displacement, distance is a scalar quantity. It has only magnitude, no direction. Let's think back to the same example from the previous slide. If an object moves from A to C to the left, the displacement might be minus 4 meters, but the distance is 4 meters. If the motion includes several segments in different directions, then the total distance is the sum of all the path lengths. Here's an example. Let's say the following diagram shows the trajectory of a ball thrown upward. If both paths have the same length, then the distances are the same, but the displacements could be very different. For example, 10 meters to the right versus 20 meters to the right. To summarize, displacement is the change in position, and it's a vector. Distance is the total length of the path traveled, and it's a scalar. Now, let's add time into the picture. To do this, we define a time interval, the difference between the final time and the initial time. This is represented as delta t, which means change in time. The formula looks just like the displacement formula, final value minus initial value. If we set the initial time to 0, then the time interval is just t. This is a really great tip that will simplify a lot of our future calculations. Once we include time, we can define speed. Speed is defined as the total distance traveled divided by the total time taken. Alright, let's do a quick calculation. For example, if an object moves from A to B 3 meters in 3 seconds, the speed is 1 meter per second. Already done the math in your head? Now let's work it out using the definition of speed. If it moves from A to C 4 meters in 2 seconds, the speed is 2 meters per second. Notice that speed does not include direction. It's a scalar and always positive. In physics, we can talk about average speed over a time interval, or instantaneous speed at a specific moment. We'll discuss that distinction in more detail later. Next, velocity. Velocity is defined as displacement divided by time interval. This means velocity includes both magnitude and direction, so it's a vector quantity. Let's calculate the velocity using the same example as before. If an object moves from A to B in 3 seconds, the displacement is plus 3 meters, so the velocity is plus 1 meter per second. That means the object moved to the right at 1 meter per second. Just a heads up. Since velocity is a vector, we always have to talk about both its magnitude and its direction. If it moves from A to C in 2 seconds, the displacement is minus 4 meters. So the velocity is minus 2 meters per second. That means the object moved to the left at 2 meters per second. Again, we can distinguish between average velocity and instantaneous velocity depending on the time interval we are looking at. Now let's compare speed and velocity one more time. Speed is a scalar. It's just the magnitude of motion. Velocity is a vector. It has both magnitude and direction. In everyday life, people often use the two words interchangeably, but in physics we need to be precise. But when we don't have to worry about direction, it's usually fine to just think of speed as the magnitude of velocity. Thinking about how much distance you cover in a certain amount of time makes speed a lot easier to understand. So when you have a complex motion that changes direction, it can be really helpful to break it down into smaller sections where the direction doesn't change. But speed and velocity are definitely different physical quantities. Here's an example. Imagine a runner going around a circular track with a radius of 100 meters. If it takes 2 minutes to complete one lap, the total distance is the circumference of the track, so the speed is about 5.23 meters per second. Check out the calculation below. But the displacement is zero since the runner ends up at the starting point. In other words, the initial position and final position are same. That means the average velocity is zero. This may sound strange, but it makes sense if you remember that velocity is defined as displacement over time, not distance over time. In general, it's not a big mistake to think of it this way. Use velocity to describe motion, and use speed for calculations by breaking down a complex path into simpler sections where the direction doesn't change. So, to wrap up, speed is distance over time, a scalar quantity. Velocity is displacement over time, a vector quantity. And that's it for today's lecture. Great work, everyone. Let's keep moving forward.